It is a stormy night, and the whole world is moving. Rain strikes the leaves. Wind bends the branches. A thin twig sways violently in the dark, shifting up, down, left, and right with every gust. And on that branch, a tiny songbird is fast asleep. Its head is tucked into its feathers. Its eyes are closed. Its body is relaxed. It looks completely vulnerable. But somehow, it does not fall. No slipping. No panics. No sudden drop into the darkness. The branch moves, but the bird stays locked in place. So here is the question, why doesn't it fall? When humans fall asleep, our muscles relax. If we try to sleep on a thin branch, we would lose balance almost instantly. Our hands would loosen. Our body would slump. Gravity would win. But birds are different. They have a secret hidden in their legs. Nature's version of an automatic deadbolt lock. To understand this, we have to look inside the bird's foot and leg. Running from the upper leg down into the toes are strong flexor tendons. These tendons connect the movement of the leg to the curling of the toes. When a bird lands on a branch and lowers its body, the leg joints bend. As the knees and ankles fold, the flexor tendons are pulled tight. That pull automatically curls the toes around the perch. The bird does not have to think about gripping. It does not have to keep squeezing. Its own body weight activates the lock. The heavier the bird settles onto the branch, the tighter the toes clamp down. Instead of using energy to hold on, the bird uses gravity itself to stay attached. That is the genius of the system. Gravity tries to pull the bird down, but the bird's anatomy turns that downward force into grip. This is why a sleeping bird can remain perched for hours. Its muscles do not need to stay tense. Its brain can rest. Its body can lower its energy use. The toes remain closed because the posture keeps the tendons locked. To release the grip, the bird simply stands up. When the legs straighten, tension on the tendons relaxes, the toes open, and the bird can take off. Locking and unlocking happen through posture. No switch. No conscious effort. No wasted fuel. Just mechanics. Some birds may also have tiny ridges and grooves in the tendon system that help the grip hold even more securely. Their toe pads and scales add friction against bark, wire, reeds, or rock. The foot becomes a high-friction interface, like a natural climbing tool. This is not just a foot. It is a biological clamp. But gripping the branch is only half the problem. What about balance? A sleeping bird on a swaying branch must stay upright while the world moves beneath it. The branch bends. The wind shifts. The bird's center of mass changes. And yet, it remains balanced. Humans rely heavily on the vestibular system in the inner ear to understand balance and motion. Birds have that too. but they also have a special sensory system near the hips and lower spinal cord, often described as the lumbosacral organ. Think of it as an extra biological gyroscope. As the branch tilts or vibrates, sensory information from the bird's body helps detect changes in position. Signals can travel quickly through the spinal cord and nervous system, helping the legs make tiny adjustments before the bird falls. This means balance does not always require full conscious attention. The bird's body can correct itself automatically. Even while the brain is resting, the balance system remains ready. A sleeping bird is not simply unconscious on a branch. It is supported by a network of mechanical locks, sensory feedback, tendon tension, friction, and reflexes. Nature has turned sleep into a physics problem, then solved it beautifully. Some birds take this even further. In Southeast Asia, hanging parrots sleep upside down, dangling from branches like tiny green bats. At first, this seems risky. Why sleep with your body hanging beneath the perch? But upside-down sleep can be a safety strategy. Many predators search along the top of branches, expecting prey to be perched above. A bird hanging below may be harder to see, harder to reach, and better hidden among leaves. Being in the strange place can become protection. Other birds, like swifts, may cling to vertical surfaces or rest in positions that seem impossible to us. Chimney swifts can sleep attached to walls, using claw structure and body posture to stay fixed in place. Again, the lesson is the same. Birds do not fight gravity with strength alone. They use design. They use angles. They use friction. They use structure. Then there are flamingos. A flamingo standing on one leg looks like one of nature's strangest jokes. Tall body, long neck, thin leg, half asleep in shallow water. It seems like balancing on one leg should be harder than standing on two. But for flamingos, one-legged standing can actually be efficient. Their anatomy allows the leg to lock into a stable position, a system sometimes described as a passive stay mechanism. Once the body is balanced over the supporting leg, the skeleton can stack in a way that requires surprisingly little muscular effort. The flamingo is not constantly working to balance. It is resting on its own structure. One leg becomes a column. The body becomes a carefully placed weight. Gravity, again, becomes part of the solution. There is also the issue of heat. Long, bare legs lose warmth to air and water. By tucking one leg up into the body feathers, a flamingo or stork reduces heat loss. One leg stays warm. The other supports the body. It is balance and thermal regulation at the same time. A sleeping posture becomes an energy-saving strategy. Birds also have another advantage. Their sleep architecture is different from ours. In humans, REM sleep can involve muscle atonia, a temporary paralysis that prevents us from acting out dreams. This is useful when lying safely in bed. But if a bird entered long periods of deep muscle relaxation while perched on a branch, it could become dangerous. Birds experience REM sleep too, but their REM episodes are often very short, sometimes lasting only seconds. That means the limp phase does not usually last long enough to break the grip or collapse the posture. They sleep in rapid cycles. Rest and readiness stay close together. A bird can enter deep rest, but not in a way that completely abandons the body to gravity for long periods. The sleep system is tuned to the demands of perching, flight, predators, weather, and survival. Even their sleeping shape is optimized. Small birds puff their feathers into a round ball, reducing heat loss. They tuck the bill under the wing to preserve warmth. They lower their bodies to reduce exposed surface area in the wind. Their feet grip. Their tendons lock. Their balance system keeps watch. Their feathers become a sleeping bag. The entire body becomes a night survival machine. And when danger appears, the system can reverse almost instantly. A sound, a vibration, a shadow, a shift in the branch. The bird wakes. The legs straighten. The tendon lock releases. The wings open. In less than a second, sleep becomes flight. This is the true miracle. Birds are not safe because they are relaxed. They are safe because their bodies are designed to rest without fully surrendering control. A hawk on a high branch. A sparrow in a storm. A flamingo in cold water. A swift on a vertical wall. A parrot hanging upside down. Each one is solving the same problem in a different way. How do you sleep in a world where gravity never sleeps? The answer is not brute strength. It is engineering. The flexor tendon becomes a deadbolt. The foot becomes a clamp. The hip becomes a gyroscope. The leg becomes a locked column. The feathers become insulation. The brain becomes a system of rapid rest and instant readiness. Nature is a master of structural engineering. So the next time you see a bird asleep on a wire, a twig, a reed, or a roof edge, do not see something fragile. See physics. See balance. See a living blueprint. See an animal that has turned gravity from an enemy into a tool. Because while humans build machines to resist the laws of nature, birds often do something smarter. They use those laws. They are the gravity defiers.